What's up everyone? I'm back with another video. This has been a video that I've been trying to do almost for the past year, is finish up repairing this HP 8557A spectrum analyzer plugin with the HP 182T mainframe. And I did a couple videos that started this. The first one was repairing the 182T, the power supply, the low voltage power supply, and then repairing the front end of this spectrum analyzer. And that's about as far as we got. The video ended with me repairing the coarse tuning knob. That had also gone bad, and that's where I left it. So I had tried repairing this thing, and I just didn't have the time. I also needed more equipment, which I did grab, and that's actually our newest addition right there, that comb generator. I'm looking forward to using that. But basically the problem with that one, and this is actually not the original, unfortunately. The original is down there, okay? Right after I did that second video, I ran into an issue where there is a procedure for basically calibrating the instrument for absolute amplitude and frequency measurements, and part of that calibration is bringing the log and linear modes, getting that relationship, amplitude relationship down, and it wasn't working. And so the procedure is you set your reference level to -20, input attenuation is at 10, at least for this unit, and you inject your calibrator signal at 250 megahertz, and you set your tuning to that, and so you start with the reference fine level at 0. Okay, so now we're at 0, and then you bring it all the way up until you've reached the top gradical line, right? Now, to start with the original unit, I couldn't bring the peak to the top gradical line, no matter what I did. And then you switch it to linear, and the linear peak should also be at the top gradical line, and it's a little off right now. It's a little higher than that, but I had it correct earlier. This peak was literally at the top, at this first horizontal gradical line. It could get no higher than that, and you're supposed to adjust the vertical gain. You go back to 10 dB, adjust the vertical gain, bring it lower. I maxed out the vertical gain, and it just wouldn't work. And I was chasing this issue throughout the unit, checking the log amplifier board, checking the vertical driver, everything, until eventually what it ended up being was a problem with the second converter assembly, which is, you can see right there, this guy. This is the first converter assembly, so that's going to have your higher frequency, higher intermediate frequency, okay, at roughly like 524 megahertz, and then this one, it's a lot lower, it's at like 24 megahertz, and so that's to provide you the best image rejection and frequency channel selection. So that's a dual converter, super heterodyne setup, and this guy was causing some sort of issue. You can make adjustments with these capacitors, tuning caps, but it just wasn't working. And I found this unit for really cheap online, and I didn't want to leave this unfinished, and so I grabbed it. it's also the LED version, so it's a little nicer. That's the mechanical version down there, if you remember, if you've seen the original. It had a couple cracked knobs, so I stole some from the original, and this one is still a little cracked, but it seems like it's working well so far. And what I thought would be neat to just kind of close this chapter so I can get this thing off this bench is just run through the performance tests, make sure everything looks okay, and then we can be done with it. All right, so thought that'd be fun. So let's do that. All right, so before we move on to the 8557A, I did want to touch base on the 182T, and this was another thing that was making doing this repair a challenge to finish, because the 182T mainframe kept dying. So I would get really busy, and then I'd come back to it, and then I'd power up the unit, and then it would die shortly after that, right? And so in the first video, focus on the low voltage power supply for the 182T, and it looks like they determine it's a 9-volt Zener. That's the issue. Replace it. It powers on. Everything looks great. It seems like that was not the primary cause of the issue. And what I have up displayed here is the IV curves for the series regulator transistor for the 100-volt rail. The negative 100-volt rail also displays similar curves, but there's clearly something wrong. This bottom trace should be straight. I mean, it should be horizontal, flat, and it's not. And this is indicating that this transistor is leaking. And if we open the base term, you can see that very clearly. This is your emitter current leakage, and it's almost at 3 milliamps. So if you look there, we're at 1 milliamp per division. So and I think we're at the collector voltage is at the max for this low voltage setting, so that's at 15 volts. I mean, that's a lot. And so that is definitely an issue, because this transistor is supposed to be regulating the voltage, and so that was probably causing some problems and causing that Zener to die. That's my guess. But so I replaced those with a suitable alternative. So I thought we'd just revisit the 182T low voltage power supply schematic really quick, and then we'll move on. But this is the series regulator transistor that I ended up replacing. This is the 100-volt rail. The 100-volt rail is the reference for the entire supply. All the other voltage rails are based off of that. This is the 9-volt Zener that has also gone bad. And what you have here is your differential comparator, which is monitoring the 100-volt rail, and is also monitoring the reference, which is being set by this 9-volt Zener. You have the ability to make adjustments at this, and both of these, the output, which comes here, is going to do its best to match that, the adjustment there. And you can see here they've got the driver to this series regulator is right here, and then you've got this fold back current limiter right here. So basically, when the voltage drop across this resistor becomes, say, 0.7 volts, this transistor is going to turn on, sinking current away from the driver transistor, which is then going to turn off the series regulator transistor. All right. Now, obviously, if this thing's leaking, that's going to affect its ability to regulate current and put strain on the other components in the circuit. So that's what I assume is going on here. Now, if this thing fails again as I'm working on it, then we'll know that's not the case. But I think that was the problem. Alright, so now we can move on to the 8557A, and I thought we'd start by just doing the performance test, see if we run into anything that's amiss, and, we'll address it if we can. So the first test is actually a frequency span accuracy test. And this is the setup that they're using, so we do have a new addition, the comb generator, timer counter, yes, we have that. Function generator, it'll depend on what frequency they need, because I think they're using this as a square. They need a square wave from this guy. Let's give this a go and also test out the new comb generator. Alright, so this is the first test, looking at the comb, 100 megahertz comb. So the peaks are spaced 100 megahertz apart, and again we're at full span, so this is 350 megahertz bandwidth. And I've moved the trace over just a bit so that the LO feed through peak is cut right right in half. And so the manual says this is what we should be getting. I don't know how they're getting numbers to those sig figs, because you can only look at this in 0.2 divisions increments, I believe. But anyway, so we should have 2.87, 5.71, and 8.57, and that looks about right. I mean, this peak is just shy of the three divisions from the LO feed through. You know, you could argue that's about 2.9, maybe 2.8. And then of course this one is at a little bit easier to see. So this vertical gradical is at 5 divisions away, and then 5.2, 5.4, 5.6, and this one is 8, so right about 8.5, so that all looks good. Alright, so for this next step, it's the comb generator's now been decreased to 10 megahertz, so the signals are now 10 megahertz apart. We're looking at 20 megahertz per division for the frequency span, and basically what they're saying is for this 17th spectral line, it should be plus or minus 0.8 divisions, is what the I guess that's how far away it should be from the 9th gradical line. That's what it seems like they're saying. And if we look at what we've got here, so this is the 17th spectral line, the 9th gradical, and we are well within that spec. It looks like it's about, maybe it's within plus or minus 0.2. So I think that is good. And once again, now we've decreased the span to 10 megahertz per division. Comb generator is still at 10 megahertz. We're still looking at the 9th gradical line, looking at this spectral line, and still we are within 0.1 divisions, so that looks good. Same thing at 5 megahertz. 9th gradical line still looking good. Now we're at 1 megahertz per division, and again, still looking good. The spec is still the same. I don't know if this is normal for one of these, but it seems that with the comb frequency lower, the amplitude is also lower, or it could be the spectrum analyzer. I don't know. I don't know enough about this to be sure, but it is accuracy for the frequency span. 500 kilohertz, still looking good. Well, that's the best I could get it for the 200 kilohertz setting, and so that is injecting a 200 kilohertz square wave into the modulation input of the comb generator. And I don't know, it's very noisy. I don't know if it's the comb generator. I mean, I was given some pretty clean signals, although they did seem to get less clean at the lower frequencies, but Could also be my pulse generator that I'm using, which probably needs some work too. Who knows? But it does look like they are lining up nicely. Alright, so that's 100. Still looking pretty good. Here we got 50. At 20 kilohertz, it's starting to become difficult to resolve the peaks. But there it is. Yeah, and so at 10, I can't really even resolve them. And so, again, I don't know if it's due to the setup that I've got going on here, or if it is an actual issue with the spectrum analyzer. I was about to move on from this test when I realized that I didn't have the sweep generator set to auto, and it does look like things cleaned up a little bit. Anyway, the spec is plus or minus 0.8 in the 9th gradical, and we're still looking okay. We'll see if it can do 5. That's the lowest. Right, that's the last test, 5 kilohertz. But it's really struggling as we get lower. Okay, alright, I mean, it's able to do it just about. I mean, and I don't know if this is typical, you know. Reference level of -80, so the signal is really low. You know, again, I've never used a comb generator before. My experience with spectrum analyzers is just this one, so. But as far as accuracy, if we look at the 9th gradical line, it's still within spec. So that's what this test is about. If we find something wrong with the amplitude or sweep generator in the subsequent tests, we'll see. Alright, so this is the tuning accuracy test, and again, we're using the comb generator. Setup is a little simpler, what this test is asking us to do is literally set the comb generator to the 10 megahertz comb. So you've got the harmonics spaced apart by 10 megahertz, and then you're literally going in increments of 10 and checking each, and tuning to that frequency, and it gives you a spec. So for example, at 20 it can be anywhere between 6.9 and 23.1. Seems kind of wide, but so for example, plus or minus 3.1, and if we move, well, actually we are at 10 right now. That looks really good. And if we just so you guys can see, the LO feed through is tuned properly. Alright, so that's good. And I'm not going to go through each of these on camera, but if we find one that's out, I'll take a look. We can take a look together. Well, all of them are in spec, and it's actually at, I'm sorry, I said 10 megahertz in increments. It's 20 megahertz. 20 megahertz increments, with the exception of the last check, 340 to 350, but this is should be 340, and it's at 337, which is right on the end there of the allowable tolerance, but still, nonetheless. And interestingly, you've got these harmonics here. I don't know if that's normal, because it doesn't show up in the earlier frequencies, but yeah, I think this is good too. Tuning accuracy looks good. Alright, so we are at the FM, residual FM test, and it looks like it's passing. What I'm thinking is, it's kind of hard to tell exactly what they're looking for, but we're looking at this peak at 300 megahertz at 0 span, so it just looks like a straight line, and I think we should be looking for any noise like this. Now, it's dropping a lot, and that's because this peak is wandering a bit. So if we go back, it's wandering away from the center vertical gradical line, but I think these guys are kind of notorious for that. So that was just me trying to adjust it, not the instrument itself. Or if they're talking about noise. on the trace, because in that case it's really clean. But yep, there it goes, coming down. So I'm not sure, but this does seem pretty typical of these instruments. But anyway, move on to the next test. Alright, now we're looking at the noise sideband test, and so again we're looking at the 300 megahertz spectral line from the comb generator, and we are looking at noise sidebands for this peak, which we've placed 10 dB above the top gradical line per the manual. And our sideband noise, we're looking at 2.5 divisions away from the signal, should be 65 dB below top gradical line, and it looks like that is being met. So that would be right on this dotted line. So that looks good. So the resolution bandwidth is actually the test I had initially started with for this, because I didn't have the comb generator at the time. So I've already done this test, I'm not going to show it, but really it's just checking to see how selective the bandwidth resolution settings are, and where the 3 dB roll-off is occurring, and that should fall within a certain spec. So for example, you know, if we look, you know, so in this case they're using the signal generator at 10 megahertz, right? And then that should fall within a certain range. So for example, here at the 3 megahertz setting, it should be falling between 2.4 and 3.6, right? So for example, we were at 2.93. They should all line up with the bandwidth resolution setting, right? So we got 1.1, 300 kilohertz, 334, 1 kilohertz, so on and so forth, and everything fell within spec. And so the next one is selectivity, where they're looking at the 60 dB point, and it's a ratio of the 60 dB and 3 dB point, and those should be within, there should be 15 to 1 at the largest, and they are all well below that. So we've got good bandwidth resolution and selectivity, so that test is good. And now we're looking at the average noise level test, which is just noise level with no signal inputted, and it should be at negative 107 dB. The reference is at 60 dB, right? Negative 60 dB. So, you know, and you would check this throughout the entire bandwidth of the instrument, and you can see here we're looking pretty good. So this line would be 105, and so we're sitting just below that, and so average noise level looks good. So I was very interested in doing this test, the bandwidth switching amplitude variation test, because I thought I was seeing some variation in amplitude between bandwidths. There definitely was variation, and in the overall variation throughout the entire all settings was greater than the spec in the manual. So for the first, between 3 megahertz and 300 kilohertz, you should have less than 1 dB, and I've got them all written out here. So 0.7, that's within, but for the overall from 3 megahertz to 1 kilohertz should be less than 2, and we're at 4.3. So yeah, and you can see there the main offenders here at 100 kilohertz, negative 1.8, and then 30 kilohertz, we're at plus 2.5. So yeah, this looks like it's going to need some adjustment, because otherwise they all look really good. And the way that they do this test so that you can calculate it easily using the display is, oh, where'd our peak go? Huh, our peak has disappeared. Sorry, our peak wandered off a bit. It's camera shy, but I got it back. And so they have you looking at the peak, the Cal signal peak, at 1 dB per division. That way you can easily calculate the difference. And you know, they start you off at the 3 megahertz bandwidth at 1 megahertz frequency span per division. Set it to 7, like 1 division below the top horizontal gradical line, and then you'll have that as a reference point, and you're calculating from that. If we go, for example, to 30 kilohertz, and 10, look, you can see we're well off the top. You can see clearly we've got some big differences. And then even if we go to 100 kilohertz and 50, so 150, you can see here we're like almost at 2 dB below. So that's what I was referring to in my notes. Everything else looks pretty good though, so this is going to require some additional adjustment, which is not included in the performance tests. Alright, so the step attenuator accuracy is the next test, and it's a pretty straightforward test. So it's testing the step attenuator, which is increments of 10 dB, and we've got a 10 dB step attenuator here to that you're adjusting to keep the input signal from our signal generator here at 30 megahertz at the same level at 6 divisions above the bottom gradical line. I've also got the frequency counter hooked up to it. This guy certainly needs a calibration. I mean, look at that. That's horrible. So we'll be looking at that again soon. But this did not change at all through each attenuation step. It stayed perfectly fine, very little deviation, and so that is great. The step attenuator in this unit, you can just see it below this board, but if we go over to our old unit, it's that guy right in here. Okay, so that is good. Looking great. Okay, so now we're doing the reference level accuracy test. And so I've already kind of gone through the log mode test. The linear mode test is next. And so this is actually at negative 100 dB. And the step attenuator is set to 90. Alright, so if we go back down, you can see how each of these, and we're looking, the reference is at the 6th gradical line, so everything looks pretty good. Oh, I went the wrong way there. Gets a bit confusing sometimes. But yeah, you get the idea. So let's do the linear mode first. Alright, so we did the log mode, we did the linear mode, and then we did the reference level fine pot as well. That one's a little bit trickier to dial in because it's not, you know, it's not like it locks into each setting, so there's always going to be a little bit of variation there, especially with this guy because this knob is just not, it's not adhering to the shaft correctly no matter what you do. It just always gets a little bit loose when you first spin it, so that complicates things a bit. But looking at all of the data I collected, the max for the fine was 0.4, and then converting for the linear mode, the difference in the division on the display, a max of negative 0.29 dB, and then for log mode, for the course reference, linear is also for the course reference knob, negative 0.5 was the largest deviation we calculated. I think this spec is for each setting, so plus or minus 0.5 dB. across all of the settings. So I think that is, we're good here with the reference level accuracy. Okay, so now we've moved on to the display fidelity test, and this is the setup. So it's taking a look at the amplitude log display amplifier by connecting a DVM to the rear panel auxiliary A connector. Wide bandwidth is selected to so the signal appears as a straight line, and that's what we're going to be looking at here. Going to be taking some measurements. Ooh, this guy is moving around a bit. Now, right off the bat, you're supposed to take an offset reading without any signal applied, and for us that was 17.4 millivolts. So you're adding that, that's what you're setting the first reading to, is 800 millivolts plus the offset. And that should be at the top gradical line. We're actually just a tiny bit below that, about 0.2 divisions below, so that's a problem. Alright, well, there's actually quite a little mistake in the manual. It says set the equipment as follows, and the amplitude scale is set to linear, but clearly that's not. We're doing the log accuracy, display accuracy test first. And actually, with no signal applied in this mode, the offset is roughly 32 millivolts, and when we plug it back in, yeah, so that's actually what it should be, right? You should be getting at the top gradical line should be 800 millivolts plus the offset. So that actually looks good. Okay, so for the first part of this test, this is the log display accuracy, and so just filling out this chart. The spec is values for each setting, theoretical from subtracted. Alright, so that's each. So for example, for this one, theoretical is 700. The offset was 32. The offset is 32, so we measured 732. Subtract those two, and you get 0. And also the difference between the adjacent was 0. So for each of these, should be no greater than plus or minus 15 millivolts, and that's correct. And then the difference between adjacent settings, or in this between step attenuations, it should be no greater than plus or minus 10 millivolts, and that's also true. All right, so you can see as we go, should be 10 dB for each. Yeah, so that first step looks good. So we can move on to the linear display accuracy check. Alright, so for the linear display accuracy test, it's very similar to the log, at least the start of it. You know, we're bringing the signal generator trace signal to the top gradical line. You know, it's going to be a straight line because we're at a very low resolution setting. And starting now, the step attenuator is a 1 step instead of a 1 dB attenuator instead of 10. And so we're starting at 0, and then we're going to bring that step attenuator to 6 dB. The trace should be at the 4th division above gradical baseline. Okay. And we are at 1, 2, 3, 4. Yes, that is correct. Now it did move a little bit, so if we, yeah, so it's right on the line. I mean, there's no change in division, which is good. So that's good. Okay, last check. I'm looking at the psychedelic TDS 754D. That's just an effect from my camera, but you really should use a power meter and power sensor for this, which I do have, but they're just not calibrated. I really have no way of telling how accurate it is, and so this is just really a very crude way of checking. But I mean, our peak-to-peak voltage is fluctuating around 13 millivolts. RMS is around 4.2, and using this dBm to volts conversion calculator, we're somewhere around 30 dBm. You know, again, it's not ideal, right? So yeah, I think that's good. Accuracy wise, we're really looking really good. It's 250 megahertz signal. I would like to send out my power sensor for calibration if it is if it can be calibrated. But yeah, so. And if there is an issue here with this signal being too low, the reference level cal is maxed out, and so I think an additional adjustment would need to be made on the first converter assembly. If that's possible, I'd have to look in the manual again, but I'm not going to worry about it too much. So yeah, and then we plug in our signal generator, which also isn't calibrated, just for a reference. So anyway, if we plug in the signal generator, however, that's looking at roughly 20 volts peak to peak. Millivolts, I'm sorry, 20 millivolts. That's actually looking pretty darn good, just from a very crude calculation. That's closer to our negative 30 dBm. So maybe there is an issue here where it's a little too low and it needs an adjustment, right? But again, this is not how you would do this. You really need a power meter and a power sensor to really accurately check this measurement. Doing it this way is certainly not the way to do it. We're just having fun. Really, this whole exercise is just for fun. This is what I do for fun. I'm not using this for anything, too critical. So yeah, but that concludes the performance tests. I mean, they've got a really crazy setup for this. Look at that. I don't know, not too crazy, but you know, they've got the power meter here. They've got a amplifier here as well. So yeah, I mean, but that really concludes the performance test. And for all intents and purposes, everything I should mention, this test, spurious response test, I could not do. Yeah, so I mean, we got through most of these tests: frequency span accuracy, tuning accuracy, the residual FM, noise, sideband test we did, resolution, bandwidth, accuracy, and selectivity, average noise level, spurious response we couldn't do because we don't have the equipment to do so. Residual response I skipped over. Frequency response we couldn't do as well due to not having the equipment. That would be one I would like to check, but bandwidth bandwidth switching we did, input attenuator accuracy, reference level accuracy, display, fidelity, and the calibrator accuracy we tried to check with what we had in-house. But I mean, the only thing that really needed a tweak based on what we checked was the a couple of the so again, the bandwidth switching accuracy. So there was those two settings, 100 kilohertz and 30, that were way out. So that we can make an adjustment with, but we'll save that for another video because I think I'd like to try to shorten the videos I do. So we'll save that for another time. But we made a lot of progress on this. This has been sitting for a very long time, and it's unfortunate that I couldn't do it with the original unit. Again, the second converter assembly had some issues in that just wouldn't allow, that was creating a significant loss in signal. All right, and so actually the second converter assembly in these is not the one that has the really expensive mixer in it. It's actually the first converter that has that really expensive mixer. You can actually still get it. I forget what part number it is. You can still buy them from DigiKey or Mouser, I'm almost positive, but they're like $300, maybe more. So not really worth it economically when you consider the cost of these today, but still. So it could be repairable, but I'm not quite sure what's causing the issue there. But anyway, we're that much closer to just closing this guy out, being done with it, and so I can move on to the next thing, put it away until it, actually I would like it to calibrate some equipment that has also been sitting for a long time that I'd like to just slap a completed sticker on. Yeah. So anyway, hope you guys found this video interesting or helpful. If you have any feedback, leave it in the comments, and I'll catch you at the next repair. All right.